individual debug and test challenge. This first session, AURIX Trace Explained, will focus on describing the AURIX on-chip trace infrastructure and should enable you to understand its capabilities. You will also illustrate these features with realistic demo examples. Now, this webinar, therefore, provides you a good foundation for the upcoming sessions, which will focus on providing solutions for specific use cases. So this is the agenda of this webinar. At first, Matthias will tell you about the basic idea and overall architecture of AURIX Trace. He will also say something about the motivation for using Trace by telling you some experiences as an AURIX FAE. Then we will look a bit more detailed into which objects within the chip can actually be observed via trace. Then we'll take a look at the flow of the trace data, what kind of trace can be generated and how to control it. And this will lead us directly into the trace configuration concept. After that, I will explain in which ways the generated trace data can be stored on chip and how the data can be output to a trace recording tool. The last topic is about timing. Since the AURIX trace offers a very flexible approach for adding time information to the trace data, it is worthwhile spending a few words on this. And for each of these topics, we'll also have a demo using the iSystem winIDEA IDE and an AURIX TC399XE device. And now I hand over to Matthias.
I want to get started on AURIX trace by first looking at a more classical on-chip trace architecture. This sort of trace architecture you can find, for instance, in ARM Cortex-based microcontrollers. The trace data is generated by dedicated trace hardware within the chip. This trace hardware is closely coupled with each core in this architecture. The program trace logic captures program flow discontinuities like branches and function calls. The data trace logic captures data written to specific user-defined locations. All these trace messages are output via some sort of trace interface. Some processors also attach a timestamp to these trace messages. Alternatively, the timestamp is added to the trace messages by the trace recorder like the iSystem blue box when captured from the trace interface. The blue box may buffer the trace data and finally forwards the data to the PC running the winIDEA trace analyzer. In comparison to that, instrumentation trace is a special form of data trace where the trace data generation is supported by some instrumented code, which needs to be added to the application code. This changes the timing behavior of the application code, so this trace method is intrusive and will not be discussed today. Now, for the AURIX family, we have chosen a fundamentally different concept. The AURIX trace architecture is centered around so-called observers. The second important aspect about this concept is that it works in conjunction with on-chip trace data buffers, which relaxes the timing requirements on the physical connection outside of the chip. The trace data is precisely timestamped on chip already, so that the external tool only needs to do data forwarding and decoding. Let's get a first glance at how flexible this concept is. There are dedicated observers for processors and buses. The user can define which objects shall be observed. A processor observation block, or short POB, can be connected to, let's say, CPU 0, meaning this POB can observe the activities of this CPU. Other observable objects are, for instance, bus masters or slaves, like memories. They may be observed by so-called bus observation blocks or BOBs. And you should note that there are typically less observers than observable objects, meaning it is not possible to trace everything, but the user has to make the selection which objects shall be traced for a specific use case. To deal with the overwhelming amount of data, the AURIX trace logic supports clever filtering of the trace events to make sure you only get what you want, so you don't need to search the needle in the haystack. This architecture will be explained in more detail during today's webinar. But before we start, let us ask the question, what this is needed for. Let me provide you with a short example from our daily support life. A support request from a customer arrives. They have sporadic issue in their system that makes the SPI internal receive buffer overflow. We check with them their SPI related software seems to be okay. Also the DMA configuration, which we check next, seems not to be the issue. With normal debugging, we don't have a clue what is happening. We suspect something is blocking the internal bus, but how can we be sure? The customer is using a TC387 device that includes a smaller trace logic called mini-MCDS. With a trace that logs the peripheral bus transactions, we could immediately see that the peripheral bus was overloaded, so the data transfer for the SPI was sometimes blocked for larger times. As a huge plus, we can also see in the trace which part exactly is blocking it. The hardware security module seems to pull some value over the bus. Then a tiny change in the software of the security module and the bus load is suddenly back to normal and the system is fine. Without having a trace capability, this investigation could have taken weeks at least, involving a lot of different experiments, managers getting nervous about schedules and delivery dates, and a lot of headache. Takeaway from this short story: Trace is a very powerful tool for quickly identifying errors and can save a huge amount of frustration and time. As we have seen, the on-chip trace logic, also called MCDS, multi-core debug solution, is pretty powerful and complex. It may actually not be affordable to be populated also on chips which go into mass production. Therefore, Infineon distinguishes between so-called production devices, which you can see here, the devices produced in large quantities, and the so-called emulation devices. So the idea is that the production devices implement all functionality needed by the actual end application, which you can see now, meaning all cores, memories, peripherals, etc., but also the debug functionality. This includes the interface to a debugger, the DAP, JTAG, or AGBT interface, and some debug logic needed for accessing the cores, memories, peripherals, but also functions like breakpoints, single step, and so forth. The whole shiny trace logic is only implemented in the so-called emulation devices you can see here now on the slide. And by the way, for a given production device, the corresponding emulation device is functionally and pin compatible. Pins which are used as trace interface on the emulation device, like AGBT, typically need to be connected to ground for the production device. As you can see in the picture, there's a larger part of additional logic on the emulation device. Those devices have all debug features: MCDS, which is the trace logic, as well as the emulation memory. Emulation memory is the on-chip trace buffer required to temporarily store the trace messages. A reduced trace logic with fewer observation blocks, less interfaces, or reduced emulation memory is implemented even on some standard devices. This mini MCDS only has one processor observation block. However, the main limitation here is the small trace buffer. The trace RAM with only 8 kilobytes of RAM. To use this, clever event filtering settings need to be applied. Let us now hesitate for a moment to fully understand that. This means with every production ECU containing an AURIX that has a debug interface and such a device, non-intrusive tracing is possible. Some emulation devices also offer a high bandwidth trace streaming interface, the Aurora Gigabit Trace Interface, or short, the AGBT. There are standard devices for some applications that even contain this logic in every device, like the dedicated driver assistance devices TC35X and TC33X. A full overview about the trace capabilities of AURIX chip is displayed on the next slide. Here you can already guess that there is either trace logic on your production chip, or an emulation device available. There is a limitation of 3 cores that can be traced in parallel in the biggest device, which means not all 6 cores can be observed at the same time. However, handling trace results from 3 cores is already quite challenging for a developer. It is essential to understand that nowadays the debug and trace functionality is implemented within the chip and the tool only uses it. It is to some degree inevitable to gain some understanding of the on-chip trace functionality. On one hand, you then understand the limitations. On the other hand, you may also realize the wide field of possibilities. And I really hope this webinar is a first step in that direction, so the knowledge what AURIX trace can do for you spreads further. For some selected devices, there is no emulation device within the same family available. In these cases, the next bigger device can be used. This is the case for a TC36X, where a TC37X emulation device would need to be used. However, there may be cases where the functionally compatible emulation device does not come in a pin-to-pin compatible package. In that case, iSystem can help you out with an emulation adapter which uses a larger package emulation device here on top and only routes these pins down to the PCB which are actually present on the production device. Okay, now I guess you have a basic understanding of the AURIX trace infrastructure and ecosystem. Now we can start looking into it in more details, handing over back to Armin.
So here we take a look at basically a maximum configuration of an AURIX device, something like a TC39 offering 6 cores, other SRI bus masters like signal processing units, the DMA controller, some SRI memory slaves like LMU RAM and OLDA. On the SVB peripheral bus, we have some modules like timers, CAN, SPI, etc., all summarized here on the peripherals, but also special peripherals like the GTM. These OTGB and OTGBM modules are OCDS trigger buses. I will come to that in more details later on, but roughly speaking, these OTGBs can be used to trace the internal status of peripherals such as interrupt requests or active DMA transactions. Okay, and down here on the bottom half, we have all the available observer blocks, 3 processor observation blocks, POB 0, 1, and 2, then 2 SRI bus observation blocks and 1 SPB observation block. The list below each observer block shows which objects can be observed, meaning traced by each of the blocks, but always only one at a time. And I will scroll through all the observers one by one, starting here with POB 0. It can be attached to either one of the CPUs 0 to 5, to the LMU 0 memory, the OLDA, or to either the OTGB or OTGBM. If we now move on to the next processor observation block POB1, you see that it cannot be connected to as many different objects as POB0. Here the selection is either CPU 1 to 5 or the OTGBM. CPU 0, for instance, cannot be traced with POB1. The processor observation block 2 is even more limited. Here basically only CPU 0 can be observed. Here on this slide we see which objects can be observed by a bus observation block, the BOB SRI1. These bus observers can basically monitor data transactions. So the unique thing about the processor observation blocks is that they can also trace the program flow of the connected CPU. The BOBs can only monitor data transfers. But as you can see here, the BOBs can not only look at SRI bus slaves, as LMU 0 for instance, but also at bus masters like SPU and also at CPUs. The interesting thing here about the CPUs is that a BOB can look at the CPU in 2 different ways, either CPU or CPU memory slave. What this means, I will explain later on when we take a closer look at processor and bus observation blocks. The BOB SRI2 basically acts in a very similar fashion, but offering some different connectivity options. The last BOB here is the observer for the peripheral bus. Here, no dedicated objects are listed. This BOB simply looks at the SPB. But as you can see here, if we scroll through all the observers and the objects they can look at, the whole scheme is not really orthogonal, and therefore it is pretty difficult for a trace tool to provide a general abstraction for it. Like the tool is doing everything for you automatically. There are just too many options, so I think for taking really full advantage of the capabilities here, it still needs a human being with some basic understanding of this architecture. And therefore, we take a closer look, first at the observers. And we start with the most capable one, the POB, the Process Observation Block. First of all, what you see here is a CPU with the CPU core and its local memories closely attached to this core. And here we have the SRI bus matrix with some modules attached to it. The core fetches instructions via the instruction bus here, so either from the instruction cache, from the program scratchpad RAM, the local program flash, or via the SRI from some global memory. Now, the program trace unit, the PTU of this POB, is of course interested in which instructions get executed by the core. However, with a high-performance core like TriCore, it is not sufficient to monitor which instructions get fetched via this blue instruction fetch bus. You have to keep in mind that not all fetched instructions actually get executed. Therefore, the PTU really has to look inside of the core, basically monitoring its execution instruction pointer, IP, which points to the address of the currently executed instruction. The data trace unit of the POB is interested in the data transactions. Now, data transactions can only occur within the CPU, like here too from the local memories here. Data transactions happen basically all throughout the system, and some of those can also be observed by this POB. So the DTU, the data trace unit, can actually look inside the CPU for the data read and writes of the local core, but also here on the slave SRI interface of the CPU, meaning another SRI bus master like another CPU accesses these local memories. And the DTU can also look at some SRI bus slaves like the LMU RAM, the older memory, and it can even monitor the status of the OCDS trigger buses, the OTGB and OTGBM. For all these monitored instruction executions and data transactions, the POB generates trace messages, which gets sent to this debug memory controller, which writes them in the end to some on-chip memory. How the data is stored on chip and how it finally ends up in the trace tool, we'll come to that later on. Here on this slide, we have a BOB, a bus observation block. It is conceptually the same as a POB, but it of course does not have a PTU, a program trace unit. Here it is only about data transactions. So the DTU of a BOB can also look at some SRI bus slaves like LMU, and it also monitors transactions of some other SRI bus masters like the DMA or the SPUs. And it can even look inside the CPU to monitor the data read and writes of the core, of the local core, and also the access of other CPUs to those local memories. Okay, so this is all about the observer blocks. Of course, there is a lot more to them, but I think we leave it at this level now. We will get to a lot more details on this once we discuss specific use cases in one of the next webinars. However, one important and also rather unique element of AURIX trace I still want to cover before we proceed to the next topic. This is the OCDS trigger bus. So basically this OCDB allows you to trace some internal status of peripherals. Such status information could, for instance, be the failure status detected by the safety management unit, a message received indication from a CAN node, or maybe the transaction status of a DMA controller. Peripherals can either provide a single status line or a set of up to 16 status signals, a so-called trigger set. The signals can be connected to a global 32-bit trigger bus, which is an input to the on-chip trace logic, the MCDS. Besides peripheral status, also interrupt service requests can be traced. Up to 4 interrupt requests can be routed to the OTGB selected by an interrupt mux. The GTM module actually has its own dedicated trigger bus. This is the OTGB-M. And in order to illustrate this a bit further, I want to give you a quick example. Here in this OTGB trace configuration, the state of the DMA controller is traced. In addition, pending interrupt requests from the 4 peripherals CAN, A to D, SPI, and timer. The DMA controller outputs a complete 16-bit trigger set, which provides the information about the activity state of both move engines and also which DMA channel is active within each move engine. Okay, now I hope you understand what kind of information these observation blocks can obtain from the observed objects. Now we take a step back and look at the entire flow of trace data. Once you have a basic idea about the flow of the data, you can better understand the overall trace configuration approach of AURIX trace. So on the very left, we start with the observed object. Let's say this is a CPU. The CPU is attached to a processor observation block, and within this POB, you see various trace generators. A data trace message generation, capturing the data transactions, a program trace message generation, looking at executed instructions, and also a watchpoint trace generation, which I do not really want to explain any further today. So all these modules generate trace information, but which of all this information will actually be forwarded to some on-chip trace storage, this is decided by this trace qualification unit. And again, this trace qualification unit is controlled by these modules here. Here, the decisions are made by a chain of so-called triggers, events, and actions. The triggers are, simply speaking, a set of address and data comparators, and they trigger like raise a flag once the monitored address or data matches with the one defined by the user. In case of executed instructions, this comparator, as said, looks at the executed instruction pointer of the core. Now these triggers can be routed to an event logic. This logic generates an event from one or multiple input triggers, and if multiple triggers are used, then they are combined with a logical AND combination. And finally, one or multiple of such events can generate a so-called action. And such an action may, for instance, be that program trace is enabled, meaning qualified to kind of pass through this qualification unit and sent to some trace storage on the chip. The action logic uses a logical OR combination of all the input events. What you can also see on this slide is a new module, the MCX, the Multicore Cross Connect. The MCX module is a similar trigger event scheme as the POB or BOBs, but it does not have any data or program trace generators. Instead, its trace data either comes from a set of event counters or, very important, from the timestamp unit. Another interesting aspect here is that actions of other modules like the POB can be imported as event inputs, and also the other way around. Actions of the MCX can be routed back to a BOB or BOB to cause some events and actions there. How this can be used, I will show in a few minutes in an example and actual demo. This is really the essential part of AURIX trace, and since it's so important, we take a closer look. So here we have this trigger event action scheme of a POB in more details. The triggers can be generated by different kinds of comparators. For instructions, we have a set of instruction pointer comparators. For data transactions, we have sets of data address and also data value comparators. The data access comparators more look at who is actually doing the access. And the fine-grained comparator is actually a very interesting one. We will describe this in one of our use case webinars, but in short, it allows you tracing a really large number of variables, like hundreds of thousands. So this can be quite useful in some cases. And we have a set of other triggers, for example, triggers from other on-chip modules like the MCX. Then we have 15 of these event units with 16 trigger inputs each. The event outputs can be routed to these actions, and for a POB, the process observation blocks, we have this kind of actions here. Trace the program flow, trace data write data, trace data write address, actually also the same for data reads, and some other actions, for instance, the export of an action to another module. For the MCX, it looks like this. The triggers can be generated either by some event counters. The counters can, for instance, count something like executed instructions or cache misses of a CPU, or also events imported from a process observation block. For example, an event if a certain variable is written with a certain value. Then we also have some dedicated triggers. These may, for instance, be a trigger coming from a device pin. The event logic then controls various actions. The most important ones are the timestamp generation and the so-called trace done control signal for the EMEM trace buffer. More about the EMEM later on. Other actions are watch point or event counter trace output, and also the export of events as triggers to some other modules. So in order to get a better feeling about this configuration concept, I want to demonstrate an example. So the use case for the example is this. Program flow trace shall be enabled basically all the time, but let's say we have a trace bandwidth limitation, and in order to avoid trace overflows, program trace shall be disabled while the CPU executes the idle task of an AUTOSAR OS. And in addition, we want to trace the data writes to a specific global variable. Both of this can be realized by using one processor observation block. For the program trace, we start by setting up an instruction pointer comparator to generate a trigger while the instruction pointer is within the address range of this idle function between address X and Y. This trigger then gets connected to input 2 of event 9, and we define that the event 9 output is true if input 2 is not true, meaning when the IP is not within the idle function. And finally, this event 9 output is assigned to action trace program flow input 0. For the data trace, we start with setting a data address comparator to trigger if a data access is done within the address range of the variable where we're interested in. This trigger is routed then to input 7 of event 0, and this event 7 causes two types of actions. It causes trace messages containing the data write address and also containing the data write value. So let's see how we can do this in winIDEA. So here we have a winIDEA workspace. We are running an AUTOSAR application on TC399XE emulation device, and we use an AGBT trace interface running at 2.5 gigabits per second. The application is already running, and I've already created a new trace configuration here and given it a meaningful name. So let's open the trace configuration to go directly into the AURIX hardware trace configuration. Here on the left-hand side, we basically find all the MCDS modules again. MCDS itself is some top-level settings. Then we have the three processor observation blocks, X, Y, and Z, the two combined SRI bus observation blocks, and the peripheral bus observation block, and also the MCX module. The INET here is an iSystem specific thing. So in the MCDS dialog, we can select to which object the POBs and BOBs are connected. Here we attach POB X to CPU 3. And for now, we ignore all the other settings here. Now we go into the POB X settings. Okay, I've already set it up again. But you can see in this, I have to admit, rather complex dialog, you'll find again the configuration scheme with triggers, events, and actions. Here we start at the right-hand side with configuring the triggers. Let's start with the program trace. We said we want to trace all code except for winIDLE function. So therefore, we need a comparator of the PTU, the program trace unit. And we want to generate a trigger as long as the instruction pointer, the IP, is within this idle function. This trigger is routed to an event. Here we pick event 9. And we say we want to generate event 9 as long as our trigger is not true, meaning we're not in the idle function. And finally, we define the action, which is we want to enable the program trace unit while our event 9 is true. And in a similar fashion, we configure also the data trace of our variable. We create a trigger on an access to this variable, route this trigger to an event, and finally this event causes two actions. Here the output of the data write address and the write data. But let's quickly change something here, just for a demo. I will change the program trace to be enabled all the time. I can simply do that by setting the action for the program trace to always. And I run a trace, and you see I get an AGBT trace overflow. This is because the CPU 3 is not much loaded yet. So we spent a lot of time looping within this idle task. And this is, as I said, quite a killer for trace. So this overflow can often be avoided by excluding the idle task from the program trace. So let's do this again. And run another trace. You see no overflow anymore, and instead we get a nice recording of the program flow and the data writes to our variable. So this car signal RPM. Okay, so let's move on to the next big topic about AURIX trace. And this is about how the trace data can be stored on chip and how it is output to a trace tool. So we have seen that the trace data is generated and qualified by the observation blocks and by the MCX module. Now, no matter how we transfer the data to the tool, the data passes through this EMEM, the extension memory. But as you can see, this EMEM is not a plain block of RAM. It is actually a bit more complicated. Parts of the EMEM are accessible by the application. The calibration memory is, as the name implies, mainly used for calibration data, for instance in engine management applications. Really relevant for trace is this TCM section and the XTM. First the XTM. These two 8 KB RAMs act as kind of a FIFO, solely used for the trace data streaming via the AGBT, the Aurora Gigabit Trace interface. So here, trace comes in from the MCDS interface and simply out again through the AGBT to the tool. More interesting is the TCM. The TCM can actually be shared by the application and by trace. Therefore, it has an interface to the SRI system bus and to the MCDS. The SPU, mainly used for radar applications, basically uses the TCM as working memory. But as you can see, the TCM is divided into so-called tiles. Each tile has typically 256 KB RAM. These tiles can be allocated to either the SRI or the MCDS interface. When used by the MCDS interface, these tiles are used to store the trace data. A trace tool can select and read out each of those tiles via the DAP interface. Here it is important to understand that the AGBT is a streaming interface, so the device itself transmits the data and the tool just needs to capture the data. In case of tracing via DAP interface, the tool needs to actively poll the fill status and read out the TCM tiles. So we basically use a debug interface for tracing purposes. But this TCM is again not just plain RAM. There are actually some intelligent buffering options, so basically two different operating modes. One mode is the storage mode. In that mode, the storage of the trace data is controlled by a trigger. This trigger has actually two aspects. One aspect of this trigger is the point in time when it occurs. And this trigger is actually an action coming from the MCX model, the so-called, as already mentioned, trace done action. This trace done has the following effect. Before this trace done, a set of TCM tiles operates in a so-called pre-trigger mode. In that mode, these assigned tiles operate in a circular buffer fashion, always overwriting the oldest trace data. Now, once this trace done occurs, the EMEM switches into the post-trigger mode, which means the remaining set of tiles will fill up with trace data until the entire TCM is full. Then trace stops, and subsequently the tool can read out the TCM tiles. CPU still continues running. And the thing is, the user can define how many tiles shall be used for pre-trigger and how many for post-trigger. So this is defined by the trigger position. So let's say you run a program trace and you set the trigger position to center, and the trace done action occurs when the CPU enters a certain function. Then half of the trace buffer will hold the program flow prior to this function, and the other half will hold the program flow after entering these functions. So one half looks kind of back into the past, and the other half looks forward into the future relative to this trigger point. Okay, so the other operating mode is the so-called upload while sampling. In this mode, the tiles are actually managed by the trace tool. At any time, some of these tiles are permanently filled with new trace data by the MCDS, and at the same time, some other tiles are read out by the tool via the DAP interface. So permanently filling the tiles from the MCDS circles around the tiles, and also the tool also circles around the tiles reading the data. And of course, the tool has to make sure no trace data gets overwritten before it got read out by the tool. This would basically represent the trace overflow. So the big advantage of this mode is that trace data can be continuously uploaded on the fly, so basically indefinitely while trace is running. But of course, this only works as long as the upload rate is at least as high as the rate new trace data is generated within the chip. So the two important factors for this mode to work efficiently are the DAP interface needs to run as fast as possible to maximize the upload rate, and the trace generation rate has to be limited to the minimum required information. And now you may actually understand why the AURIX device offers such a sophisticated trace qualification scheme with its triggers, events, and actions. On one hand, you want to effectively use the available trace storage, and on the other hand, you want to allow the upload while sampling run via the DAP interface. Okay, so I assume the mode which is a bit more difficult to understand is the storage mode with trigger position and this pre and post trigger mode. Therefore, we want to give you a practical example. In this demo, we want to investigate why our application restarted. So apparently we got some sort of reset, but we don't understand why. Therefore, we want to find the root cause of the reset by means of trace. And we do that by utilizing the storage management scheme of the EMEM. So how can we do that? The concept is this. We set the trigger position to center, meaning we assign 4 TCM tiles to storing trace data previous to the trigger and 4 tiles for tracing after the trigger. Okay, and what should we use as a trigger now? The easiest option here is to generate the trace done action when the application restarts, meaning when the CPU 0 executes the startup routine again, basically. And by the way, I don't think there is any way to debug this case with a non-trace method like CoreStack, for example. You know, after reset, there is simply no call stack anymore. Everything really starts from scratch. So let's look at the use case here. So here we have our application running, and at some point we will get this reset, the application reset, which means that we will restart execution from the reset vector. And I can simply demonstrate this by setting a breakpoint at the reset vector, this address. And then we have to wait a little bit. Now you see the reset has occurred and we are stopped at the reset vector address. And you can also see this, the call stack window is basically empty, since we started the program from scratch and there is simply no call stack yet. So this is not really of any use and we need to apply different methods, meaning trace. So let's try this again using trace. First, we take a look into the trace configuration for this use case. As said, we set the trigger position to center, and as trigger event in the POB, we choose the startup routine, so our application start address here, this label _start. So the PTU of our POB recognizes the CPU entered the startup routine. We set a trigger for that and route this trigger to an event. And this event is exported from the POB via this action here. This POB action is imported again into the MCX and connected to this event 1. And now this is the important thing here. This event generates this action to control the trigger in time for the EMEM, so this famous trace done action. So before we get this trace done trigger, the first half of the EMEM runs in the circular mode, and once we get the trigger, the EMEM switches to this post-trigger mode and permanently stores the trace until it is full. So let's start the trace, and you see the tool doesn't get any trace data yet, but the chip internally already generates trace data, which goes into the EMEM in this FIFO mode. So now we can analyze what happened here. This red cursor here is the trigger point. So the reset must have happened a bit before that. After this trigger, you basically see the startup of the system after the reset. So when the init task, for example, is executed here, this is where the OS starts executing again. So let's look backwards to the left from this point on to see what was executed and actually caused the reset. For finding out what the reset cause was, we utilize a pretty handy feature of the profile timeline, which helps us sorting all the functions here according to time when they were executed. You know, by default, all these functions are sorted alphabetically. This is when you click on this field, for example, then you see these are all sorted by alphabetically. A very nice feature now is this bar here. When you click this, all the functions will be sorted according to their call times when the function were entered or when they were exited. And this is always relative to the cursor position, this black cursor position. For example, when I set it directly at the trigger point and I click this button, if I have it this little icon pointing upwards, this means that the functions will be sorted according to the entry. So you see exactly after the trigger, after entering the startup routine, what functions were executed in timely order. What we are interested here for finding the root cause for the reset, we want to actually look back in time. So we want to order the functions according to the exits. So you can do this. And now we can look back in time and see always which function have been exited last, like going back in time. And we see the last one of the last function we executed were, for example, okay, terminate task, this OS task here, and within this OS task, if you zoom in a little bit further, this runnable, for example, this terminate task, by the way, this may be there because this function was not really terminated, so this never actually terminated here, but so the proper code was actually executed here. And if we set the cursor here into some of this runnable, for example, we can always see the corresponding instruction which we executed in this view. So they are synchronized to each other. When I move the cursor here, also this will move, and this will put me to the exit of this runnable. And for example, if I go from there and scroll back a little bit, I will find some code which says like, oh, assert application reset. Okay, so this seems to be the point where the software itself asserted application reset. And if I look a bit back further, I find some code which says like, okay, if this certain variable is set to 1, then assert this reset, or can read data, which indicates that someone might have been triggered by receiving a can signal. And this seems to be the case because we also come here from the com receive signal, also indicated here to the function execute before this runnable is a com function. Then we enter this runnable, and then we see apparently this runnable performs a reset caused apparently by a request coming from external, from another ECU that wanted this ECU to be reset for some reason. So this is basically the way how we could identify the root cause for this reset. And just to mention here, you may wonder why there is so much time difference between the reset which occurred here and the startup routine. This is actually the time when the bootloader, the internal boot ROM, executes. And from here to here, this is basically the time the OS requires for starting up and executing the first tasks. So with this, we have pretty much covered the basics about AURIX trace. However, there is one more AURIX specific aspect about trace, and this is the business about how to add timing information to the trace. So let's get back to this picture again. Fundamentally, there are two timestamping concepts. In one concept, the trace data coming from the chip are timestamped when they get captured by the trace tool. This is typically used with lower performance microcontrollers. With higher performance microcontrollers, however, the timestamp is usually added already on chip. This is because the propagation delay between the trace data generation and when the data appears at the trace recording tool is not constant due to the heavy on-chip buffering. AURIX also uses on-chip timestamping. On one hand, this is because it is needed due to its performance. The CPU is running at 300 MHz, but it is mainly needed because AURIX is also built for storing the trace data on chip. This means the trace data are actually read by the tool much later compared to the time when they got generated in the chip. And what is also important to understand, the timestamps are transmitted to the tool in form of a separate message stream. This means the timestamps are not attached to each trace data message, but timestamps are generated by a dedicated unit, the timestamping unit, TSU, and transmitted with dedicated trace timestamp messages. And to make things even more complicated, there are basically two different timestamping concepts, the so-called ticks and the so-called relative timestamps. So what is this and when should I use what? So before I explain what ticks and relative timestamps are, I need to quickly show you this slide with the timestamp counters. The important ones are these two, the TSU prescaler and the TSU emulation counter. The first one, the TSU prescaler, is clocked typically by the system clock divided by 24. Based on the reload value programmed into the TSU prescaler, it generates a periodic trigger, this TSU TC trig. And this trigger can be used to periodically emit a 32-bit relative timestamp message, the TSU rel. And this TSU rel is basically the snapshot of this emulation counter. The emulation counter runs at the MCDS clock, which is normally half of the CPU clock. So in most cases, CPU clock is 300 MHz, thus the MCDS runs at 150 MHz. As I said, the TSU rel timestamp is output at the rate defined by the TSU prescaler. Typical periods for this rate are listed here. For instance, if you set the prescaler to the minimum value 1, the resulting timestamp output rate is 160 nanoseconds. So every 160 nanoseconds, a timestamp message will be generated. If you set the prescaler to 8, the TSU rel message is generated every 720 nanoseconds. So why is this relevant to me as a user? This I'm trying to explain with this slide here. So in the MCDS configuration, you decided to use a TSU rel timestamps, and you set the prescaler to, let's say, 4. This means that every 400 nanoseconds, there will be a timestamp message. Now, over time, you may have these periodic timestamp messages, and kind of randomly in between, the actual trace data messages may occur. For example, some program flow messages. And all the messages will first be buffered on chip and after some time uploaded to the PC. Now in this case, the tool will take the trace data messages, program trace for example, and interpolate them equally in between the timestamp messages. As you can see, this may result in some inaccuracy, kind of a timing jitter, but that's the best the tool can do in this case. The tool cannot know when exactly in between the timestamps the trace message actually occurred. But it also means the smaller the distance between these timestamps, the more accurate the trace measurement. And this is exactly where you as a user come in again. You can decide what is more important for you. Either ensure an accurate measurement, but at the cost of high trace bandwidth, because more frequent timestamp messages simply consume trace bandwidth or trace memory space. Or you rather sacrifice accuracy for the benefit of a longer trace recording. You can decide this by adjusting this prescaler value. Now, a tick is a very compact timestamp message, which basically represents one MCDS clock cycle. I know there are multi-ticks and so on, but let's ignore this for now. So every single MCDS clock cycle, the TSU generates one tick message. One tick message means one MCDS clock cycle has elapsed. At an MCDS clock rate of 150 MHz, this means every 6.66 nanoseconds, one tick message. So these two, let's say, program trace messages are 6 ticks apart from each other, meaning they occurred with a time difference of 6 times 6.66 nanoseconds equals to 40 nanoseconds. The messages are stored like this in EMEM, and when the trace messages are uploaded to the PC, the trace tool is able to reconstruct the exact timing with an accuracy of this 6.66 nanoseconds. There is no tool interpolation, timing is just accurate. As you can imagine, this tick approach consumes quite a lot of trace bandwidth. But the difference compared to TSU rel with the prescaler of 1 is actually not so bad. So per default, I would always start with tick-based timestamping. Only if this should not work, then change the TSU rel and tune the prescaler value. Now I want to quickly demonstrate you these timestamping options, and after that, we are actually finished with this webinar. In this demo, I want to demonstrate the effect of using two different types of timestamping, ticks and TSU rel. For this, we look at, again, two different use cases. The first use case is that we trace into the on-chip EMEM. We simply run the trace until the EMEM buffer is full. The idea here is that we look at how much trace, meaning basically trace duration, we can fit into the buffer when using different timestamping configurations. The second use case uses the upload while sampling concept. So the aim is to have continuous and basically infinite upload of trace data to the PC via the DAP interface. Here we also play around with the timestamps for getting a feeling about how it affects. So let's start with tracing into the enum buffer. So just for information again, the emem, or actually all 8 TCM tiles of the emem, provide a total of 8 times 256 kilobytes equals 2 megabytes of RAM. As I said, these TCM tiles can be allocated to either the application software or to trace. Here we want to allocate all 8 tiles to trace. I can do that in the CPU configuration dialog. For a demo, we do an AUTOSAR OS and runnable trace by means of data trace. So we add trace instrumentation code to the OS tracing hooks. In this case, we use the vector microsar OS timing hooks, and for runnables, we use the RTE VFB tracing hooks. For a much more detailed description how this works, you can check out our AUTOSAR profiling webinars on our website. We start by using tick timestamps. The timestamping is configured in 2 dialogs. First, on the main MCDS dialog, here we need to choose the source of the timestamp. So we say timestamp source is ticks. In addition, we need to go to the MCX dialog, since this is where the action gets created for outputting timestamp messages. So here in MCX, we simply define that ticks are always enabled. And by the way, this trace done is set to always, as we immediately from the start want to enter this post trigger mode of the image, just filling it up. So this is it. We run a trace. And we see we can fit about 2.35 seconds into the buffer. So let's do this a few more times. We get a rather consistent result, this 2.35 or 36 seconds of total recording time. Now let's switch to TSURL. Here we define the timestamp source to be TSURL, and we define a value for the prescaler. Let's start with the maximum accuracy, meaning prescale value of 1. Then we go again to the MCX. Here ticks is disabled, but instead we enable TSURL again with always. And we define that the TSURL timestamp message is output on every prescaler period. For that, we use event 8 and connect it to the TSU timestamp counter trigger. And route this event 8 to this action to create the TSURL timestamp message. Here we can actually use a pulse or edge on the event 8. Okay, so let's run a trace again. You see, the trace duration is significantly reduced to about 126 milliseconds. So let's do this again. See, still the same result. Now let's change the prescaler to, let's say, 8. And trace again. Okay, you see this 478 milliseconds that we can fit the trace buffer. So as a result, I guess here it is much better using ticks as a timestamp source. Obviously, ticks produces simply less data compared to TSC rel timestamping. And actually, tick provides a more accurate measurement. So I guess we should see a similar effect when we look at the upload while sampling use case. A very important parameter of upload while sampling is, as mentioned before, the dub frequency. Here we use a moderate dub speed of 30 MHz. We could actually go up to 160 MHz. The chip and the tool would actually support this, but maybe not your ECU board layout. Also, the DUB-E interface is not used here. So let's run a trace again using ticks. Let's look at our configuration for upload while sampling. First, in the recorder settings, we define to use upload while sampling. Then in the MCDS settings, we enable ticks. And in the MCX, we also enable tick generation. And in addition, here we set this trace done to never. Basically meaning that we permanently use the EMIM tiles in kind of a FIFO fashion. Okay. So we run a trace. And we actually stop after 2 seconds, but only because I told the profiler to do so. So to automatically stop after 2 seconds. It could actually run infinitely long for hours or whatever. So switch to TSC rel again. Prescaler is set to 1 for a start. And you see trace stops already after like 140 milliseconds. Let's play around with the prescaler again. Set it to 4. And trace. Yeah, okay. About 1 second already. Let's change it to 8. And trace. Okay, now we also get to the profiler timeout of these 2 seconds. Okay, so the other knob you can of course trim around, of course, is the dub speed. I mean, if this is really possible on your board, but you see, especially for the tick timestamping, there is still some headroom in the trace bandwidth, upload while sampling trace bandwidth, so you could potentially add some additional signals you want to trace into your trace configuration. But I guess you got the message here. I would always recommend to use tick timestamping whenever possible. It is simply most efficient in terms of trace bandwidth, and it also gives you the maximum of time measurement accuracy. Basically, the only situations where tick is not applicable is when we need to correlate the AURIX timestamp with some external time base. For instance, when we also trace the CAN bus or some external signals via one of our add-on trace boxes. So, I hope this webinar did actually provide you some better insight into tracing on an AURIX microcontroller. I know this was probably heavy stuff for software engineers, but I mean, we do embedded software, and here I think knowing the underlying hardware does make a difference. But in case certain aspects are still unclear, this is a chance now for raising the questions. And we will continue this series with much more use case oriented sessions. So thank you very much.
So, hello again. Thanks, Armin. Thanks, Matthias, for this very detailed demonstration. It was very interesting, but as you said, also very detailed. So now it's the chance to raise your questions. As most questions so far reached us, yes, this session is recorded, will be recorded from the very first second until the very last second, and it will then be published on the iSystem YouTube channel. After the session, you will receive a link to the YouTube channel. If you want to receive the dedicated link, please feel free to drop us a message to webinar@isystem.com. So Matthias, Armin, it's your part again. I'd like to start with a question I have basically. So you mentioned a lot of times DAP interface. How about the JTAG? So I think a lot of customers also have a JTAG interface on their board. Is this also all possible with a JTAG connection too?
So basically, yes. But if you're using the JTAG protocol, basically it will be very, very, very slow. The nice thing about AURIX is that on the JTAG connectors, you have the DAP pins as well, so you can also use DAP on the same physical pins, basically. So all you need is a small adapter, basically, and then you can use DAP, which gives you a lot more data rate.
Yeah, maybe I can add something from a tools perspective. If you use JTAG, the only option for tracing is that you upload the trace data from the EMEM. So you store the trace data in the EMEM, then you can upload it through JTAG. That's possible. Use cases, like I explained, this upload while sampling is only possible through the DAP interface. And actually, we, as a tool vendor, we don't see any benefit in using a JTAG instead of DAP. So our recommendation is simply use the DAP interface. Then you have all the options. You have much more performance. It's a robust interface, so there is no reason for using JTAG on AURIX from our tools perspective.
So software guys, fight for DAP interface on your board, and this goes out to the hardware guys. Don't even think about JTAG.
Exactly.
Yeah.
Yes, and another question is about the emulation device. When I want to use an emulation device, do I need to change something, or can I just solder it, or is there anything I need to be aware of?
So the idea behind the emulation device is that you can just solder it into the existing footprint, basically. So, but maybe Armin can explain better, because that's basically something that iSystem provides as a service.
Yes, I mean, what we can do, for example, if you have some problems designing a board for both production device and emulation device, we have the experience working with emulation devices since we also developed the emulation adapters. So we could, for example, review the board layout and give you some recommendations how to terminate, for example, IGBT pins which are not used when you use a production device. So that's a service we can offer to you. But as mentioned in the webinar, typically those specific trace pins not used on the production device need to be some sort of terminated. But other than that, they are pin and functional equivalent, so you don't need to change anything in your software. The software runs one-to-one on either emulation device and production device. Also, timing is the same, so it's really partly. I mean, it's actually the same silicon. The emulation device is just more than that. I hope this answered the question.
Thanks. I see that people don't see the cloud symbol, so please let me check that. You will get for sure the presentation on which way ever you will get it. Back to the Q&A, back to the technical questions. MCDS is a question. Has MCDS Mini or Mini MCDS the same meaning as MCDS Lite?
No. So the MCDS Lite is so basically we have the full MCDS, which is the biggest configuration. Then we have the MCDS Lite, which is a bit smaller and has only 2 observation blocks. And then we have Mini MCDS, which has only 1 observation block and only 8K of trace RAM. the nice thing about the mini MCDS is that on some production devices, so meaning the ones used in serious production in large volumes, it's even available on those devices. So you can basically open up the case of the ECU, connect it, and then do trace on your production ECU with the mini MCDS.
One thing I want to add is on the mini MCDS, due to its small buffer, it's also a plain RAM. Let's put it this way: you can only write data into this buffer, and then trace is done. It's not such an intelligent thing like the EMEM with TCM tiles. You can't do upload while sampling. This is not possible there. So it can trace, yes, but with a very limited amount of what you can store on the chip. Whereas on the MCDS Lite, the nice thing there is those devices come with a full EMEM implementation. So this upload while sampling is possible. It has, of course, much more storage, like I said, like 1-2 megabytes. And some devices also come with an AGBT interface. So in terms of trace performance, it offers the same performance as the full MCDS. It just has less observers. That's the only difference. Okay.
Thanks. Another question is about an emulation adapter for TC397XX. So Matthias, this goes out to you. Is one available? Do you need one for a TC397XX at all?
Yeah, as you already suggested, no, for a TC397XX you don't need an emulation adapter. So maybe let me clarify that emulation adapters are only required or are mainly required for QFP packages and things like that, because they don't have the additional pins. And for BGA packages, you have within the same family an emulation device that you can solder one-to-one in the same footprint. And for the 397XX, this is compatible to the 397XE, which is the emulation device for this one. For 397XX and XE, you only need to be careful because both use EMEM, and the 397 there it is available for the application. So the application and the tooling need to basically make sure they don't use the same part of the emulation memory, because otherwise that's, of course, that will lead to conflicting accesses.
So the customer doesn't need to spend money, right, for an emulation adapter. Good news.
Yes.
Bad news for us.
Another question is it possible to view CPU 0 and CPU 1 using a POB 0 simultaneously?
Yes, this is possible, and I mean, yes, it is. In general, it's possible with an MCDS or an MCDS Lite. With a mini MCDS, it would not be possible because it only has one observation block. But it depends basically on what device you have. If you have a device that is a 397, you could do it because it has 3 processor observation blocks. And if you have a 387, which has only a mini MCDS, then you could only view one processor at a time, basically.
But maybe just to clarify, you can observe one CPU with one processor observation block. It's not possible to have one processor observation block and look at 2 CPUs. Not possible. You can only connect it to one. Within the CPU, then you can observe different things like program flow, data transactions. This is possible within one observation block, but you attach it to one CPU and this is it.
But at the end, it definitely depends on the device the customer is using. So I think this needs some more offline discussion, as said, depending on the exact device you're using.
Yes, you should.
Yes, sorry.
Yeah, it's okay. I mean, you should know how many observation blocks you have in the MCDS of your particular device. Then you can judge how much you can trace, how many different things you can trace.
Okay. Another one is, if I want to route a trigger to an event, is it specific or is the trigger mapped to any event?
you cannot map any trigger to any event input. There is some chip internal, not really filtering, but it's simply not connected. Like it's not completely orthogonal. You cannot connect everything to everything. But it's so sometimes you have to pick specific triggers, specific comparators to route it to a specific event, and these events that can be routed to actions. So sometimes you just need to scroll a little bit through all the event configuration then to find the correct trigger that you want to use for a particular use case. Yeah, this is just a matter of practice, but it's not, as I said, not completely orthogonal. Yeah, I mean, if there are issues, let us know. If you can't make a proper routing or can't generate your use case, we are here to help you in that end. But you see, if you open the event configuration, then you see what kind of triggers you have available, and then you can pick the corresponding trigger in this trigger column of the configuration.
Exactly. So winIDEA automatically filters the possibility, so it doesn't show anything that is not configurable.
Yeah. In short, yes. Sorry.
We have enough time, guys. No issue. I mean, the next question goes out to you. Is there a specific license needed if I want to experience and have all this trace feature available in winIDEA?
Yes, you need the trace license.
Yes.
Exactly.
Yeah. So for a configuration, the debug activation key is the limit or the basic what you need. And for having this analyzer, what Amin showed, there is a trace activation key available. You can check that in your blue box or send us your serial number and we will check that for you.
And in terms of trace hardware, maybe the tool we recommend is an IC 5700 to be used with an AURIX device. You can then attach it directly to a DAP interface if you can live with a lower DAP speed of maybe like 20-30 megahertz. If you need to go above that, for example, if you use upload while sampling, OS profiling, that we recommend a DAP active probe, then you can run it if your hardware allows it at 160 megahertz. Or the biggest configuration obviously is the HBT interface, because then you can either extend your blue box with an DAP active probe or an HBT active probe. So we can still reuse the base unit, but extend it with a trace interface you need for your use case and your kind of trace performance that you need.
But I think a lot of customers also have an IC 5000 on the desk. So this is also possible with an IC 5000, but with some limitations, right, Armin?
Exactly. You can connect directly from the IC 5000 to a DAP connector with a like standard ribbon cable kind of, but this has a limitation of like how fast you can run the DAP clock. It again depends on your hardware, but typical values are something like 20-30 megahertz, I would say. This is simply then your limitation in terms of upload speed for this upload while sampling, for instance. You can still use it for if you store the trace data in the EMEM, then it really doesn't really make a difference. You can upload this also through a lower speed DAP interface, but yeah, it's more optimized for storing the data on chip rather than for high performance upload while sampling.
And as you mentioned before, the HBT interface in connection with the IC 5700, when does a customer need the HBT instead of a DAP interface? Maybe you can refer to some use cases.
Yeah, the main use case for HBT is when you want to do program flow trace. Program flow trace, like to give you a rough figure, each CPU generates something like 60 megabytes per second data when you do a full program flow trace. For example, if you would want to do a full function profiling, for example, then roughly that's what you need. With upload while sampling, for example, you can only achieve something like maximum peak upload rates of like 30 megabytes per second, whereas an HBT has around 270 megabytes per second. So you see you need to match the internal chip trace generation rate with the capability of the trace interface, and simply for doing full unconditional program flow trace, you need the trace bandwidth of an AGBT interface, and it's also be capable to do a program flow trace of 3 CPUs in parallel. That's possible with an AGBT. You may also do some additional data tracing, depending on use case like OS or something. Then data trace also generates quite a large number of quite some data. An AGBT just gives you the biggest flexibility, but the must-have use case is really program flow trace to function profiling or things like code coverage analysis, which is also based on program flow trace. For example, OS profiling with this task profiling, things like that. This can typically be achieved with upload while sampling with an TAP active probe. But if it comes to program flow trace, then an AGBT is the right selection.
If you want to go for software coverage or something like this, and maybe I should add that working with an AGBT is a lot more fun than with the other interfaces because it's simply much more responsive.
It's like driving a Porsche or a Golf or something, right?
Exactly.
Is an AGBT available on all devices, or is there a difference, Matthias? Where do I get that?
You get it on all emulation devices, and in the overview contained in the slide set, there's also an indication where you have the AGBT interfaces. So on the dedicated ADAS devices, you have it everywhere, as well as on all emulation devices.
Okay, thanks for that. Another question goes again out to Armin. Are we able to get the data trace result into Canopy from the winIDEA analyzer?
What you could do, for example, you could do a data trace, do the recording, store the data within winIDEA, within our analyzer, and from there you have different exports formats available. Can be simple comma separated, for example, or XML, but we also support, for instance, MDF4 output format, which is the format then the vector tools typically can seamlessly import. So you can definitely import an MDF4 export directly into Canopy. So that would be my recommended way. We also have features like winIDEA can also work as an XCP server. So you could, for example, use Canopy as an XCP master and winIDEA as the XCP slave, and it will read out, sample the data from the chip according to this XCP configuration. So which is more like an ongoing sampling process as opposed to recording, storing, and then output or export the data in MDF4. So these two options, I would say, exist in conjunction with Canopy.
Okay, and it seems it's the last question. How can you activate the profiler timeline or make it visible as seen in the webinar? Where do I need to click?
I need to open the analyzer, which is a specific view. So whenever you create the workspace, then the corresponding analyzer view is available in the main menu under view, and then workspace name .trd. That's the trace document. This will open the analyzer window, and then you have all the trace features available. But for using the analyzer, you need a trace license, basically.
Yes. So if you need some additional help, please reach out to us, and Armin will show you.
I mean, I guess
way again.
It's a good hint. We can add this into the next webinar, how to actually open the analyzer window, and then you will see it also live, how to do this in winIDEA. Good hint.
Yep. All right. In theory, we have some time left, but we don't have some questions left. So obviously, you were very clear. And so let's then come to an end for this webinar. Thanks. Yeah.
Maybe because just to clarify things, I mean, the configuration option you've seen here seem to be very complex, and it can be complex. I mean, this is just what the chip is. Sorry. But my point is, what I want to make it, if you have a simple use case, you don't have to go through this rather complicated MCDS configuration. So there are other options in winIDEA or in the analyzer to configure AURIX trace For instance, you can just work with a profiler, and in the profiler, just say, I want to have this and this variable or code profiling done by the analyzer. Then the winIDEA tries to do the hardware configuration in the background for you, and you don't need to go into this complex configuration dialogue. So this is usable for, let's put it, say, typical simple use cases, like just doing a program flow. You just click profile code and this is it. So this is an option. And there are also some trace. There's also trace wizard, which will like a step-by-step guide to the configuration that you need. And also we have so-called trace templates, which are like pre-done configuration, which can be parameterized. For example, which functions, which data do I want to trace? This is also an option. Then you don't really have to go deep into this MCDS configuration dialog. But we wanted to show you the MCDS because we want you to understand the full capabilities of this chip, because it's rather unique, and this is the intention of this webinar. That's why we go so deeply into this MCDS configuration.
Also, I think, I mean, if you have a use case in mind and you don't know how to configure it, you can always contact one of us, your Infineon or iSystem counterpart for support, as we usually work quite closely together, and I think we can quickly identify what's possible and how to do it for you.
Exactly. Yep.
Yeah, absolutely. So that's it. No more questions left. Thanks for sharing your knowledge, Armin and Matthias.
You're welcome. Pleasure.
And yeah, this was the Q&A session. Sorry that the download did not work. We will contact all of you and send you the PDF presentation directly, and we will improve on that. But before you leave, I would like to give you some additional information and ask for your feedback. So besides the questions tab, you have a polls tab. Please give us your feedback, how you like the webinar, and if you enter in the questions tab again, some topic suggestions, this would be very much appreciated from our side. Feel free to also check our online trace tutorial, our application notes, and also, of course, our YouTube channel, where this webinar is hosted and a lot of others are already available. And if you want to, feel free to register to our newsletter, then you get, for example, webinar invites automatically. And as Matthias said, if you have any questions, feel free to reach out to one of us, to your Infineon counterpart or to your iSystem counterpart. If you don't know who this is, just send us an email to webinar@isystem.com and we will take care. One last information I would like to give you. Session 2, as already mentioned several times, of this Infineon iSystem TriCore AURIX webinar series takes place on March 25th. It's also a Thursday, so 2 weeks from now, 4 weeks from now. And there we start exploring specific use cases. Matthias will also be here again, and from iSystem side, it's systems engineer Felix Martin. And for all Spanish-speaking guys out there, next week, March 4th, the Thursday, we will have this webinar in Spanish language. So thanks for attending. Thanks for your questions. And again, thanks, Matthias. Thanks, Armin, for your time, for your knowledge. And bye from my side. Take care and hope to see you soon in the next webinar. Bye.
Yep. Bye-bye.
Bye.